Hi, I'm Choi from Seoul National University. I'll talk about our work, Balanced Spherical Grid for Egocentric View Synthesis. This is joint work with Sang-min Kim and Young-min Kim. Neural Radiance field has demonstrated its incredible performance on visualizing a bounded scene. In this work, we propose a practical solution to reconstruct large-scale environments while taking advantage of the vast speed of recent advances. In short, EgoNeRF adopts an efficient and practical capturing setup to reconstruct large-scale scenes, which we call egocentric video. To represent a large-scale outward-looking scene, we use balanced spherical grid as Radiance representation. We also propose an efficient resampling technique for camera resamples without allocating additional coarse grids. First, we'll talk about our practical setup. There are a few methods to capture large-scale scenes. First, commodity RGB or RGBD camera is often used to capture large-scale indoor scenes such as in ScanNet. RGBD cameras have a price advantage, but the small field of view nature lengthens the camera trajectory, which makes it difficult to capture large scenes in a short period while scenes are in static. Next, some methods use spherical multi-camera rigs. It is high cost and inaccessible to non-expert users. In contrast, we use egocentric video with an omnidirectional camera to capture environment. By rotating the camera attached to a stick, we can capture the entire scene within a very short period of less than 5 seconds. These videos are samples of our synthetic omnidirectional video dataset named OmniBlender. They are short videos captured by a virtual omnidirectional camera. Note that the camera trajectory is short relative to the scene size in the egocentric video. Also, we captured real-world scenes with Ricosetta omnidirectional camera. All of the datasets are publicly available. Now let's look at the balanced spherical grid, which is our Radiance field model for egocentric captured scenes. While NeRF and most NeRF variants assume inward-facing views, most views are outward-looking in a large-scale environment, especially for egocentric videos. While the conventional Cartesian grid is efficient to represent bounded scenes looked at inward-facing views, they are not suitable for outward-looking views. Since the Cartesian grid has a uniform grid size regardless of distance from camera path, they have insufficient resolution for nearby objects and extra backend for far objects. They also suffer from a non-uniform ray grid hit ratio in the outward-looking scenario, which is indicated by the orange shade in the figure below. However, the spherical grid nicely fits the egocentric video capture, and it naturally resolves the aforementioned limitations and also guarantees a nearly uniform ray hit rate. While the regular spherical grid nicely fits the outward-looking views, there are some limitations. First, the non-uniform angular grid size. In particular, the grid size near the two poles is extremely small, creating undesirable rendering artifacts. Also, the uniform grid partition in the radial direction is not scalable to unbounded scenes. To resolve the non-uniform angular grid in the conventional spherical grid, our balanced spherical grid adopts the yin-yang grid in angular partition. We use quasi-uniform half of the original spherical system and combine two of them. These two grids are referred to yin and yang grid, which have identical shapes and size. In radial part, we make the grid along the r-axis increase exponentially. The resulting cell has similar lengths in angular and radial direction. Similar to other grid-based methods, EgoNeRF also considers the explicit feature grids as the mapping function instead of NeRF's MLP. We have two grids, namely density grid and appearance grid. The density grid has a single channel that stores the explicit volume density value, and the appearance grid stores three-dimensional neural appearance features. The density and color can be obtained by trilinear interpolation in the grid or decoded by a tiny MLP. Furthermore, we decompose the feature tensors into vector and matrix vectors allowing TensorRF, and it allows us to reduce the space complexity. Now let's look at how EgoNeRF makes camera ray sample with resampling method. Since the occupied region in the 3D space is sparse, it is very inefficient to take ray samples uniformly. Therefore, the original NeRF proposes a hierarchical sampling strategy. While other grid-based methods maintain a dedicated data structure for coarse grid, we exploit our density feature grid without allocating additional memory for the coarse grid. The coarse grid can be obtained on the fly during the training by applying the average plane corner on the density grid. First, we sample coarse samples from the coarse grid, and then we additionally sample fine samples from the original fine density grid with importance sampling. Now let's take a look at how we optimize EgoNeRF. Following other works, we minimize the color discrepancy between volume rendered images and the training images. Additionally, we optimize the environment map to handle the infinite far regions such as skies. You can see the effect of the environment map in the figure below. Removing the environment map in the outdoor scenes shows blurry artifacts in infinitely far regions. The view synthesis errors across the training step are indicated in the figure below. Our approach achieves fast convergence speed, which benefits from the grid-based approach. And with our balanced spherical grid, we can achieve state-of-the-art performance in the OmniBlender dataset. These are the free view rendered videos at our OmniBlender scene and the corresponding bird's-eye view 2D map indicating camera path. Cartesian grid-based methods including DVGo and TensorRF suffer from blurry artifacts in the nearby objects since they don't have enough resolution, and MIMNeRF 360 often misses the thin objects due to their proposal network. In contrast, our approach is able to render clear images both in close and far regions. To conclude this talk, EgoNeRF takes very practical and casual input to capture large-scale scenes, namely egocentric video. EgoNeRF takes advantage of grid-based methods with its fast converging speed, and our balanced spherical grid tailored to the outward-looking scenario improved performance in large-scale scene. You can download our data and code, and also you can find additional results in the following webpage. Thank you for listening to our talk.